Welcome back. We'll continue our discussion about uh, Shannon Channel coding theorem for AWGN channel. So let me just recall what is our model. So we have input. It is in discrete time, so we call it xk. This is the input to the channel. This input gets corrupted by additive noise nk, and what we receive at the output is yk. Okay, so we can write yk is xk plus nk. Okay, so let me remind you that actually input process is continuous in time. It is x of t. Noise is also continuous in time. It is n of t, but we are sampling it. Okay, and we assume that this input is band limited. It is a bandwidth b hertz. So and to sample it enough so that we are able to recover it, we need 2b samples per second. This is a minimum sampling rate per second. Okay, so in time period t, how many total samples we can have? 2b times t. This will be denoted by k. So if we are communicating for a time period t, then the number of samples is 2bt. So we can write then this k is equal to 1 to up to capital K, where capital K is 2bt. And this noise nk, first of all, it is additive, and we assume that it is white. White means that its power spectral density what is power spectral density? It is power per frequency. That is in simple words I can say. So if you see the plot of power spectral density of this noise, it is constant. Okay, now since we are working in a bandwidth of b hertz, so on this scale it is b and minus b. So this is the power spectral density of this noise. Okay, let this height be n naught by 2, where n naught is some constant. So this is 2b. So the total average power will be n naught by 2 times 2b, which is n naught b. Okay, and we know that if we see the noise nk, we assume its distribution to be Gaussian, and we assume its mean to be 0, and variance sigma square. Variance of this noise is simply expected value of nk minus mu square. Now since mu is 0, so it is expected value of nk square. But if you see, expected value of nk square is also the average power, which is n naught b, and this is same as variance, so sigma square. Sigma square is equal to n naught b. This is another observation. Now we have input xk, output yk. Yk is also random, but mind it, see, xk is discrete time signal, but takes continuous values. This is very important. Xk can take any value. It is not, it can take only, it is discrete in time, that is defined at particular time, but it can take any value. Similarly is nk, discrete time but can take any value, yk also. So they are all continuous random variables. And how much information yk contains about xk, that is defined by mutual information. Okay, and we also have in previous class defined this thing, so I will again write it. It's called information capacity. Information capacity, it is defined as the maximum value of mutual information between the input to the channel, that is xk, and the channel output yk, and with respect to what, over all the distributions of xk. It will be clear. So it means that you have this I of xk yk. You want your rate. See, this is information capacity is related to the rate. It's actually maximum value of the rate, data rate, we can say. So you want it to be as max as possible. But what is in your control is just input distribution fxk of x. So you want to maximize it with respect to the input distribution. And this is denoted by the C. This is the definition of channel capacity. Now we have a constraint such that, subject to constraint. What constraint we have? That the average power of input symbol, which is expected value of xa square, it cannot exceed some fixed value p. Practically it means that your batteries are finite, right? You are using batteries, or you are using any energy source. You have a finite energy source. You cannot have infinite energy. So at most what can you take is, if you want to utilize maximum energy, you can at most take expected value of x square equal to p. Okay, so this is the best you can do. But you cannot pick up a average power more than p. You are allowed because you have finite batteries. So now let's go step by step. So we use definition of I of xk yk, right? We can write it as differential entropy of yk minus differential entropy of. So I warn here to those students who haven't revised it, whatever I have taught till now, it will be painful for them. Go back to the video lectures, revise the definition of entropy, conditional entropy, differential entropy again. Okay, if you don't, then these lectures will be painful. Now what will be, let's compute one by one. So yk is xk plus nk. Now you are computing differential entropy of yk given xk, right? So this quantity has an operational meaning, that suppose someone tells you what xk was. Okay, what was transmitted, someone tells you, that is what it means by given xk. So when someone tells you what xk was, so there is no uncertainty left about xk. Now in yk you have two terms, xk and nk, which are both random. But if someone discloses what is xk, xk does not remain random at all. Now the whole randomness, uncertainty, is only because of nk. So h of yk given xk can be written as h of nk. Okay, because conditioned on xk, someone tells you what xk is, some genie tells you what xk is, so there is no uncertainty left about xk. Now in yk the only uncertainty left is because of nk, the noise. So this is differential entropy of noise. And you know, this noise we have assumed is Gaussian, zero mean, variance sigma square, right? And we have derived in last class the differential entropy for Gaussian random variable is half log to the base 2 pi e sigma square, right? Now we are left with another quantity. So this is step number 1, step number 2, we are left with h of yk. H of yk is h of xk plus nk, correct? Now you want to maximize the mutual information to find the channel capacity, the maximum rate. For this you need to maximize this h of yk minus h of yk given xk, and you want to maximize it with respect to the input distributions, right? Now this is maximum value of h of yk with respect to input distributions, minus the second term is constant, it is half log to the base 2 pi e sigma square, because this is simply h of nk. Okay, so now to maximize the mutual information, you need to maximize the entropy of yk. You need to find the maximum value of this, right? Now here are the facts. We have done one important result. This and differential entropy is maximized when yk is Gaussian, right? We have done it when yk has Gaussian distribution. Now yk is equal to xk plus nk. So nk is Gaussian. For we need y for maximizing h of yk, we need yk to be Gaussian. Nk is Gaussian. The only way yk will be Gaussian is xk should also be Gaussian only. Okay, and see, we are maximizing with respect to the distribution on x, and what it says is entropy of yk will be maximized only when distribution of xk is Gaussian. Okay, now comes the question of what should be the variance of this. You see, variance, now you are choosing xk to be Gaussian. So mean, you can always assume 0. Mean has no meaning, so mean is just an arbitrary thing. Now what will be its variance? It will be expected value of xk square. But we know that we have a constraint on the average power, which is same as expected value of xk square, that should be equal to p. So variance of this input should be chosen as p, or in other words, xk, which is normally distributed 0 mean p variance, will maximize this entropy, hence will maximize the mutual information. Okay, so maximum value of h of yk, which is same as maximum value of h of xk plus nk, this happens when when xk is Gaussian, and the value will be half log 2 pi e. Now it will be variance of xk plus nk. We have derived that for a Gaussian random variable, the differential entropy is half log 2 pi e, variance of that. Now here we have sum of two Gaussian random variables, hence sum of the variance, which will be half log to the base 2 pi e. Variance of xk is p, variance of n is sigma square. Okay, so hence maximum value of mutual information with respect to input distributions is half log to the base 2 pi e p plus sigma square minus half log to the base 2 pi e sigma square, which is half log to the base 2 1 plus p by sigma square. Okay, so this is the famous, you know, uh, channel coding theorem, and we call the unit as bits per channel use. What does channel use means? Basically, you are for every information bit, you are transmitting multiple code word bits. So every time when we transmit one bit, we call it one channel use. We transmit two bits, we call it two channel use. Three bits, we call three channel use. Okay, so this is what means. Now, how many times channel is used? So channel is used for transmission of k samples of the process x of t. We told you initially that we are basically sampling it, and for how much time? For t seconds. Okay, so we can say that information capacity per unit time is actually k by t, number of samples per divided by total number of time, which is 2bt by t. Okay, hence the overall capacity will be 2bt by t times half log 1 plus p over sigma square, which is b log to the base 2 1 plus p, and sigma square is n naught b. This also we have already shown. And now the units will be bits per second. So capacity is b log to the base 2 1 over p by n naught b. This is the famous celebrated information capacity law. Information capacity law. It means that for a signal operating in a bandwidth b with a power constraint p, the maximum rate at which you can transmit the information is given by this c, b log of 2 1 plus p by n naught b. Okay, is very remarkable result. So I will keep this lecture this much short. Give some time to it, try to understand the steps. In next part of the lecture, we will try to understand some of the operational meanings of these terms, what capacity means, and this will motivate us our further study of other techniques in digital communication.